Ordovician Silurian extinction. The Ordovician Silurian extinction was the first of the 5 major mass extinctions and one of the deadliest. It occurred in 2 distinct pulses and wiped out approximately 85% of all marine species, especially invertebrates. Life at this time was almost entirely aquatic, so this event had a profound impact on Earth's oceans. The leading cause was global climate disruption, likely triggered by the formation of the supercontinent Gondwana near the South Pole. This movement initiated a major glaciation event. Ice sheets expanded rapidly, locking up large amounts of water and causing a dramatic drop in sea level. As shallow marine habitats vanished, reef communities, trilobites, brachiopods, and graptolites suffered massive losses. The first extinction pulse was driven by global cooling and sea regression, while the second occurred when the Ice Age ended. Melting glaciers released trapped freshwater and nutrients into the oceans, possibly triggering anoxic events. Oxygen depleted waters that suffocated remaining marine life. Some species adapted by retreating to deeper or more stable environments, but most could not survive the swift ecological shifts. Unlike later extinctions, this one didn't affect land animals. There simply weren't any yet. Recovery took around 20 to 30 million years, during which entirely new marine ecosystems formed in the Silurian period. Late Devonian extinction. The late Devonian extinction wasn't a single catastrophic event, but a drawn-out crisis lasting up to 20 million years. It occurred in several waves, ultimately eliminating around 75% of marine species, particularly those in shallow reef-like environments. While not as sudden as later mass extinctions, its prolonged environmental stress reshaped life on Earth. This extinction targeted reef-building organisms, especially stromatoporoids and tabulate corals, which had dominated the oceans since the Silurian. Entire reef ecosystems collapsed and didn't recover for over 100 million years, until modern coral reefs evolved in the Mesozoic. The likely cause was a combination of global cooling, ocean anoxia, and possibly asteroid impacts or volcanism. A leading theory suggests that the rise of land plants played a crucial role. As vascular plants spread across continents, their root systems broke down rocks and released nutrients like phosphorus into rivers and oceans. This triggered massive algal blooms, which upon decomposition depleted oxygen levels in marine waters. The result: widespread anoxic zones, particularly in deeper seas. These dead zones suffocated marine life, especially bottom-dwelling invertebrates, trilobites, and jawless fish. Shelled animals like ammonoids and brachiopods also suffered major losses. Interestingly, this extinction had little impact on land life, which was still in its early stages of colonization. However, it cleared the way for new types of vertebrates. Lobe-finned fish, the ancestors of amphibians, survived and eventually ventured onto land, setting the stage for the rise of tetrapods, 4-limbed vertebrates that would evolve into amphibians, reptiles, birds, and mammals. The late Devonian extinction acted more like a filter than a sudden purge, slowly reshaping ecosystems over millions of years. Permian-Triassic extinction. The Permian-Triassic extinction, often called the Great Dying, was the most catastrophic extinction event in Earth's history. It obliterated over 90% of marine species and around 70% of terrestrial vertebrate species. No other extinction has come close to such a complete collapse of global ecosystems. The primary driver was likely massive volcanic activity in what is now Siberia. This episode, known as the Siberian Traps, involved one of the largest volcanic eruptions in the past 500 million years. The eruption lasted for nearly 1 million years and released vast amounts of carbon dioxide, CO2, and methane, CH4, into the atmosphere. The greenhouse gases caused rapid global warming, with temperatures rising by as much as 8 to 10 degrees Celsius, 14 to 18 degrees Fahrenheit. As oceans warmed, they lost oxygen, a condition called marine anoxia, leading to widespread suffocation of aquatic life. In some regions, the seas turned euxinic, rich in toxic hydrogen sulfide. This deadly gas may have even outgassed into the atmosphere, poisoning terrestrial ecosystems. Additionally, the volcanic emissions produced acid rain and ozone depletion, killing forests and damaging DNA in exposed organisms. The combination of heat, chemical stress, and oxygen loss triggered ecological collapse across every environment on Earth. On land, Dominant amphibians and early mammal-like reptiles known as theropsides largely vanished. Insects, which had previously thrived, experienced their only known mass extinction. Coral reefs disappeared completely, and trilobites, which had survived for over 270 million years, went extinct. Recovery was painfully slow. It took 10 million years for biodiversity to bounce back. During this time, Earth's ecosystems were dominated by disaster-tolerant species like Lystrosaurus, a pig-sized herbivore that made up nearly 90% of some fossil communities. The evolutionary vacuum eventually allowed new groups to emerge, most notably archosaurs, which gave rise to dinosaurs, crocodilians, and pterosaurs. Triassic-Jurassic extinction. The Triassic-Jurassic extinction marked the end of the Triassic period and the beginning of the age of dinosaurs. It wiped out approximately 70 to 75% of all species, eliminating many large amphibians, mammal-like reptiles, and early archosaur competitors, clearing the way for dinosaurs to dominate the Jurassic world. The exact cause is still debated, but strong evidence points to massive volcanic eruptions linked to the Central Atlantic Magmatic Province, CAMP. These eruptions occurred as the supercontinent Pangaea began to break apart, releasing vast amounts of carbon dioxide and other greenhouse gases into the atmosphere. This triggered rapid global warming, accompanied by ocean acidification and marine anoxia, the same deadly combination that plagued earlier extinctions. Ecosystems collapsed as temperatures spiked, disrupting food chains in both the oceans and on land. In the oceans, many marine reptiles and invertebrates like ammonoids, bivalves, and brachiopods suffered heavy losses. On land, early mammal-like reptiles and several archosaur groups went extinct, while small, fast-growing dinosaurs and early pterosaurs survived and rapidly diversified afterward. The extinction was relatively swift, occurring over just 10,000 to 20,000 years, and acted as a biological reset. Dinosaurs, having survived this event, faced far less competition and quickly diversified into the dominant terrestrial animals of the Jurassic period. The Triassic-Jurassic extinction represents a turning point in vertebrate evolution, setting the evolutionary stage not only for dinosaurs, but also for the first true crocodiles and eventually early mammals, which lived in the shadows during this time. Cretaceous-Paleogene extinction. The Cretaceous-Paleogene extinction, also known as the KPG extinction, is the most famous of all extinction events. It marks the dramatic end of the Mesozoic era and the extinction of the non-avian dinosaurs, alongside around 75% of all species on Earth. It was a sudden, catastrophic event that reshaped life permanently. The leading cause was a massive asteroid impact. Geological evidence points to the Chicxulub crater in present-day Yucatan, Mexico, measuring over 180 kilometers wide. The asteroid, roughly 10 to 15 kilometers in diameter, struck Earth with an energy release equivalent to billions of atomic bombs. The immediate impact vaporized everything in its vicinity and sent a shockwave around the globe. Debris ejected into the atmosphere formed a global dust cloud that blocked sunlight for months, possibly years, triggering what's known as an impact winter. This caused photosynthesis to collapse, killing off plants and disrupting entire food chains. Simultaneously, there is evidence of intense volcanic activity in the Deccan Traps, modern-day India, which may have worsened the environmental fallout by releasing more greenhouse gases and toxins. The extinction was particularly devastating for large-bodied animals, especially on land. All non-avian dinosaurs went extinct. Marine reptiles like mosasaurs and plesiosaurs also disappeared, along with many types of plankton, ammonites, and flying reptiles. Some groups survived and went on to diversify. These included mammals, birds, the only surviving dinosaurs, crocodilians, and many amphibians. Plants also rebounded relatively quickly, with flowering plants becoming dominant in the post-extinction ecosystems. The aftermath of this event allowed mammals to rise into ecological niches left vacant by the dinosaurs, leading eventually to the evolution of primates, hominins, and, millions of years later, humans. The Anthropocene extinction. Unlike the previous 5, the sixth mass extinction isn't confined to a geological period. It's happening right now. Often called the Anthropocene extinction, it is driven by human activity. not natural disasters or cosmic events. Since the rise of agriculture and industrial civilization, species extinction rates have accelerated to levels 100 to 1,000 times higher than the natural background rate. It's estimated that Earth is currently losing dozens of species every day, many of them undocumented. The drivers are well documented. Habitat destruction through deforestation, urbanization, and agriculture is the most significant cause. Tropical rainforests, home to over half of the planet's biodiversity, are being cleared at alarming rates. Overexploitation through hunting, fishing, and poaching has decimated countless species. Iconic animals like the rhinoceros, pangolin, and numerous large fish are on the brink due to illegal wildlife trade and unsustainable harvests. Pollution also plays a massive role. Plastics, heavy metals, and synthetic chemicals have entered every ecosystem, from the deepest ocean trenches to the Arctic. Pesticides like neonicotinoids disrupt pollinators, while industrial runoff fuels dead zones in oceans. Invasive species, introduced either accidentally or intentionally by humans, outcompete native species and upset ecological balances. Examples include the Burmese python in the Everglades and zebra mussels in the Great Lakes. Perhaps most significantly, climate change, fueled by human-induced carbon emissions, is altering ecosystems faster than species can adapt. Rising temperatures, shifting rainfall patterns, melting ice, and ocean acidification all contribute to biodiversity loss. Coral reefs, for example, face total collapse within decades due to bleaching events caused by warming seas. Scientists have warned that if current trends continue, we could lose up to 1 million species in the coming decades. Entire ecosystems, such as coral reefs, Arctic tundra, and rainforests, are at risk of collapse. What sets the Anthropocene extinction apart is its cause: us. It's the first extinction where a single species, Homo sapiens, is responsible for triggering global biodiversity loss. And unlike previous extinctions, which unfolded over thousands or millions of years, this one is moving at the speed of human progress.